Hi everyone. So my name is Aryan, and this video is going to be first of many, and I'm going to do an entire playlist on distributed systems. Um, this is the first time I'm actually recording a video for YouTube, so I might make a lot of mistakes. So please just bear with me, and yeah, I hope you enjoy. So I want to start off this series by going over one of the most critical kind of topic of the entire of a distributed systems, that's basically replication, and that's about how you know master slaves databases work. So for that, the practical question that I need to ask you is, there are times when you actually see outdated data. For example, you might post a photo on Instagram, but a lot of your friends might not see it instantly, right? Or when once you make a transaction, sometimes what happens is that money is deducted from your account, but it's still not shown in other accounts basically. So after watching today's video, you'll be able to understand why that happens and how can we actually tackle it. So to understand this, I will first want to okay, so the way I'm going to structure this is that we'll go step by step. So as a person who doesn't know anything about distributed computing, you should be able to build on the incremental knowledge that will both basically gather over this playlist, and you'll be able to understand a lot of these complicated concepts in depth. So the first thing I want to tell you is okay, so we'll be discussing these topics today, and the thing that I want to start with is a WAL, and this basically means how is data written to a database. Okay, so okay, we are going to start with something called um, W sorry WAL. This is called write ahead log. Okay, so you know what a database is, right? It's in the end it's just a software that takes in your data, puts it in memory. Memory is physical, right? Now you know there are two types of memories. So one is RAM, and one is your disk memory, which is actually your computer storage, right? So RAM, you know, it's quite fast. It actually works in 10 to the minus 9. So that is basically nanoseconds. Writing to disk is kind of slow. So that takes about 10 to the minus 3ish milliseconds or something. Now let's say that someone sends a request to a database, right? And we want to store it in the DB. What exactly happens is what we are trying to understand over here. This does not happen that the request comes in and you store it directly in DB, right? This does not happen because writing in database, writing in the actual disk is a slow process. You cannot do that. What if you are updating a million rows here, right? You cannot update all those million rows in that database at the same time. It can just freeze up the entire DB. So that's not how we do it. Also, if we are updating the DB, what if the DB crashes or electricity goes off? What happens to your DB in that case? Can be a lot of scenarios that are made out of here. So the first thing that happens when you write to a DB is that the the changes that you're making to the table, they're actually logged in something called a log, which is append only. Now this lives on the disk. Okay. Uh, so basically you are appending whatever changes you are writing to the DB on disk, but in an append only fashion. Now you might ask that, hey, but isn't this slow, right? Uh, I told you, right, writing into disk is a pretty slow process, but writing the changes to the DB on a log that is append only is not a slow process. The key feature here is append only. The thing is that, so imagine this is your memory. Okay, this is your entire memory, and there is, now this is physical memory I'm talking about, right? There is a part of your CPU that actually writes data into this, right? it is extremely easy for it to jump to the end of this file and continue writing content over there. That is really fast, even on disk. What's not fast for it is to jump in between this memory. So if I tell you to edit a file, that is going to be a time intensive computation. But if I tell you to write at the end of a file, that's actually going to be pretty straightforward, because the CPU path that's going to write to the disk is actually, it just has to jump to a straight place to another place which is predetermined. Making random jumps across memory is not efficient, but making jumps to the end of the file is. Okay, so this is what the idea that I want to drive home is this: whenever data comes, we this is the first thing that happens when data comes. So it gets logged onto the disk. Now once that data is onto the disk, even if light goes off, electricity goes off, our DB crashes, we can recover that data because we have the log. We can actually build out the table from that log, right? Once the data once the data lives on the disk, it is then sent to RAM. Okay, now RAM, it's quite fast and it's volatile, right? So if the system crashes, RAM is lost. But even if RAM is lost, the data is still present on the disk, which is your WAL, your write ahead log, and you can reconstruct data from that. Now after some time, from RAM, what happens is that from time to time, a lot of data gets collected, and that is flushed directly to your actual DB, which is your disk. So this is the entire workflow of data coming in. Just a second. Yeah, this is the entire workflow of data coming in. Let me just write that as well. Data incoming. Okay. So once again, once let's say you write something to a database, right? That is going to get appended to a log on the DB. Okay. Now that log lives on disk. So even if the DB crashes, you still have that data. And then that goes to the RAM. Now once it goes to RAM, and after a certain amount of time, the RAM kind of compiles up all of these batches of transactions that it do to the database, and that is written to the disk at some time efficiently in future. An important thing to understand over here is that once that data is written to the write ahead log, okay, this is weird. Why is this coming like that? Okay, once that data is written to the write ahead log, it actually sends an acknowledge back to the user. So now we can send that data to the user that your data is safe with us. So this is how basically how a val works. Okay. So yeah, this is how data is written to any database, right? So this is clear. Now let's build up on top of that. Okay. I want to talk about a problem. So imagine that okay, I want to bring across the topic of what master slave databases are and why they even exist and why they are such a big deal. Okay, so imagine that we are in this world, and okay, let's just do I have a browser with me? Just a second. Let me bring a browser actually. One second. This will just make it a little pleasing to the eye to watch, honestly. Dude, why is it so slow? Why is it so slow? World map. Okay, whatever. Let's see that okay, I might actually. I have terrible internet connection. I am inclined to actually drop this entire thing. Okay, man. Yeah, okay. Sorry for that. Okay, so what happens when, let's say you are in India, right? And you have your customers all over the world, and you want to write something to a DB, and you want those customers to be able to see it. Okay, what makes more sense? That someone in US, they query a database in the US, or they query a database in India, right? Of course in the US, right? Because the database is closer to them and they'll get the data quicker, right? Also, another thing, let's say you are in a read heavy system. Now I want to tell that usually all of the systems that we design today are read heavy. So for example, let's Instagram, right? You usually post maybe sometimes a year, but you scroll a lot, like you watch a lot of reels. So you are reading other people's content. So that's a read heavy system. So let's say Justin Bieber uploads a photograph. Now that photo is going to be viewed by millions of people across the world, right? So millions of people are going to read a photograph, but only a single person is going to write to the DB for that photo. So this is a read heavy system. So what happens in these systems is that it is very beneficial that you have a database on which you can write to. So you can write to a database, and there should be some databases from where you can read. Okay, why is that? Because there are just more people who want to read stuff, right? As I told you, Justin Bieber is a single person who will make a request to this write database. How do I get this thing to be straight, dude? Can I make it straight? Arrow type. Okay, yeah, great. So Justin Bieber should be able to write to a database, okay? But there are millions of users, right, who just want to see his photograph. These people should only really need to see the photo, right? So they should only query the databases from where they can read. So basically we should have two different databases. On one you can write, on one you can read, right? And the read databases, they should be more in number, because usually these operations are read only. More people want to read the content. So this is exactly what a master slave database is. These write to databases, these are called master, and all these databases are called slaves. So this is slave 1, this is slave 2, this is slave 3, and yeah, this is slave 4. Now imagine that slave 1 is actually serving people, let's say in Europe. So people in Europe are actually hitting this database, right? Slave 2 actually serves people in Asia, right? And so on. Let's say this master database exists in San Francisco, right? So Justin Bieber basically uploads a photograph. His photo goes to a server in San Francisco. Now that photo is actually sent to all these slave databases, basically. And once they are sent there, any person in Europe region, when he wants to see the photo that Justin Bieber uploaded, he will query the slave database, right? Why not master? Because that's how we reduce the load on master, right? We can write a lot of queries, a lot of writes will go to master, but for reads, if everything starts going to master, I think it will crash, right? You cannot add so much spike to a single database. So this is basically how reading works. This is a master and these are slaves. Slaves will have the exact same data as master, and yeah, all the reads are actually done on slaves and all the writes are done on master. This is a very simple example. This is a very simple example of what you called a master slave system, or you can call it master replica system. So this is how a lot of these systems are developed in real world, which are read heavy systems. Now an interesting thing to think about is that if you upload a photo to master, right, it will take some time for it to go from master to all other slaves, right? Of course, because, well, we are not God, right? It will take some time. So there is a small lag if you think about it. there is a small lag, let's say 2 milliseconds lag to get to slave 1. There can be a lag of 10 milliseconds, let's say, for some reason to go to slave 2 because maybe the server in Asia is too busy, right? Now this means that a person in Asia, a person in India might not see that photo posted by Justin Bieber, even if he has posted it, even if Justin Bieber can, if he told the world that he has posted a photo, but I might not see it. And this is the exact reason why sometimes you just don't see stuff that actually exists in the world, right? This is the reason. You did write to a database that was a master, but when you were reading content, you were reading from a slave that did not have that data yet. That will get that data if you refresh it or wait for some time. You will find that data, of course, but after this lag is complete, right? This lag is called replication lag, right? And it can vary. The another term that I want to introduce you with is called eventual consistency. That basically just a big term that basically means that every slave will eventually be consistent with each other. Every slave will eventually have the same data as master, which is true, right? Of course, because anything that master does, that is kind of sent to all the slaves, and slaves basically store that data more or less, right? So this is how master slave replication really works. Okay, now let's go to the next topic. Yeah, okay, we can go in more depth and I can explain how this actually happens. So this wall system, basically, okay, in a high level stuff, in a high level scenario, what happens if you write data to master, it gets written to master's wall, right ahead log. Once that is done, we send an acknowledgement back to the user, hey, that we have the data in master, and that basically the log of master, the wall, that is streamed across all the slaves. And once that is streamed across all the slaves, these slaves replay them and actually mimic the master in the same way. So this is done through walls actually. But yeah, now I would want to take this idea further, right? When master is sending that data to the slave, okay? Let me see if I can actually copy this. Oh, I can actually do it over here as well. Okay, let's delete this acknowledgement. Now I want to ask a question. Let's say we send a, some data to master, right? I want to update the value of a table's row, for example, and that data is sent to all these slaves, right? What should I tell the user? Okay, so here's a user. One second, let me also remove this. Right, so here is a user. Now this user is going to this user is going to run an update query on a DB. This user sends that query to master. Okay, now master makes a change to its own database, and then it will send that value to other slaves, right? When should we tell the user that their query was successful? Is it when the master has done the change, or is it once the master has sent that change to slave 1, or is it when master has sent those changes to all the slaves and it has received answers, acknowledgements from all the slaves, and after that, right? So let's think about this. Let's say that the master actually sends the data to the slaves, waits for their acknowledgement, that slave 1 says, hey, I've received that data, slave 2 says, I've received your data, and so on, and then master sends back the acknowledgement to the user. This is called synchronous replication, basically. In this case, once the user gets the acknowledgement, we are guaranteed that when the user will do a read query on any of the slaves, the user will get the right information, right? Because all the slaves do have that information already. But what happens? But okay, what is the drawback of this whole scenario? The drawback is pretty simple, right? What happens if slave 2 is down? It could be, right? Slave, what happens if just this lag turns out to be, let's say, 100, right? what happens if slave 4 is down? Master might kind of just it just might keep on waiting for a response from slave 4, right? But it just won't receive it, so it will never send this acknowledgement to the user, and the user just might keep on waiting for the acknowledgement even if all other 3 slaves do have the data. This is the first simplest thing that can happen, right? Now this lag can increase, that can be a problem. So the problem with this is that this is a slow system. The user will have to wait for acknowledgement from all the slaves, right? We can make this faster by actually having an acknowledgement by just one slave, or let's say 2 out of the 4 slaves, or 3 out of the 4 slaves, and this is actually called a quorum, and I'll make a video of this in the future. But yeah, this is the main idea of synchronous replication basically. But okay, what if we want to make it faster? What One way to do that is actually, once you send the data from user to master and master writes it to its DB, what if I send an acknowledgement back to the user instantly? It says, hey, I've received your data, and it then sends the data back to slaves. Now this is called asynchronous replication. This is extremely fast because master does not wait, excuse me, master does not wait for confirmation from all different kind of slaves, right? The drawback from this is of course that if the user tries to read from different slaves, it might not see its data or might see old data, right? And but the good thing about about this system is that it's extremely fast. Master is not reliant on any of the slaves. Any slave might die, but the system will keep continuing, right? So this is what is the difference between synchronous and asynchronous replication basically. Now I would like to show you this in practical. Okay, I want to just really hammer this thing that this is not instantaneous. Master and slave, they are like, they could be across the entire world, and there is real lag between that. Okay, there's a very small demonstration that I'd like to show to you. Okay, so we have a Docker compose file. Okay, in this we are going to spin up 2 containers, a primary and a replica, and we are just saying that a replica should follow the primary database. It's a slave, as you can see. The important thing to understand, just a second, just a second. Okay, I think I'm missing something, but yeah. Yeah, okay, so this is your replica and this is your primary, and this basically just follows the primary database. And what we are trying to do over here is that we are going to run the container so that these databases are live. Then we are going to use a tool called pgbench. It's basically used to, is it pgbench or not? Just give me a minute. It's pgbench. I think it's pgbench. I guess so. I might be wrong on this, but yeah, we will basically use a tool that will hammer the shit out of the master database, right? It will do a lot of queries on master. Master is going to write those queries on its wall. This wall is going to be sent, it's going to be streamed to the replica database in our local host. Okay, this is not across the world, but in our local host. And I want to show it to you that even in a single host there is lag, or there's actual lag that you can see. Okay, so for that, what we will, one second, what we can do is open a terminal. Okay, let me see. So let me see if there are any other containers running. Okay, I have a Kafka container. Let's actually start this up. Yeah, so docker compose up. You could, I think there's a command called I think D. So D should basically do this in background. So let's just skip it. I just want to be very sure that if it works correctly. Okay, so both of these should be working. Let's open a new terminal. Docker ps is just a command that tells you the live containers you have. Okay, so we have 2 containers running. One is replica and one is primary. Cool. Now I have some commands. that I would like to copy, because I don't think I can ever remember these commands, but yeah, sure. So yeah, in this we are going to set up a new container called this replication demo pgnet. We are basically going to run pg bench over here, and as you can see, check this out, right? We're going to just run pg bench over here, and this is going to init the database with a lot of tables basically. Yeah, so once we are done with that, I am going to use another tool, the pg bench tool, to actually run for 120 seconds, that's 2 minutes, and we are going to make 32 concurrent connections to the database, and we are going to hammer the master database with a lot of updates and data, right? And we will see if we can see any lag, if we can see any replication lag on this database, right? Before that happens, I want to give you a query. Postgres, yeah. So this query basically, as you can see, 0 bytes behind. This query, we are getting into the shell basically, and we are printing these columns from the pg start replication database, the table, right, in our primary database. So this is a table that Postgres gives us, that gives us a lot of information about the lag basically, right? If you just open it again, you can see that there is nothing at all, right? There's no lag, all the fields are empty. I'm not quite sure why it came over here, it should not have, but yeah, let's try it again. Yeah, it's quite empty, right? Cool. Now we will start hammering the master database with some data. There we go. Now we have 32 clients and they are hammering the master database. Now let's run that same query again, and see if we get any lag. Oh, there you go. You see that the replica is 816 bytes behind master. That means it doesn't have the data. So what could happen is that I write an update query on master. If I read that query from replica at the same time, I might see an old value. Now this can be problematic to a lot of folks, but it again depends on how you handle it, right? So you can check out this Docker file, you can check out these commands. It's pretty straightforward. There's nothing really to kind of explain in this Docker compose files, but yeah. Now the next question, the final question basically becomes is that, well, okay, master sends data to slaves. Are there ways through which we don't read old data, we don't read stale data? And there are a couple of ways for that. So the simplest way will be to not have any slave and do all reads on master, right? And that this might sound impractical. I mean, who would do this? Because the reason to have slaves was in the end. 1 second. The reason to have slaves in the beginning was that to not do this, right? But what if we do it for specific users, right? At times it happens that, for example, let's say I write a comment on someone's reel. That comment might not be visible to different people across the world. But when I query the database, what if I query master just for myself, okay? And everyone else queries slaves for themselves, but I query master database for my comment, okay? I'll see the updated comment. I'll not think that I've gone crazy because I made a comment and it got deleted. No, I'll see my comment, and other people will see my comment when it's replicated to them. In this case, this is basically something called sticky. Let me see the exact name. It's called sticky read, this thing. Let me change the color. Okay, we will now see tips to get of this bad stuff. Sticky reads. So this basically means that reading from the primary DB instead of the slaves for some time. Okay. The second thing we can do is Well, what if in a request we could tell our system that, hey, okay, so if a certain request is critical, right, and we really need the updated value, we can just tell the system that we want to read this particular request's value from the master, and the other values basically that are not quite critical. For example, if I want to see the number of likes on a reel, right, we can tell that we can read it from slaves basically. So this whole thing is called per request consistency. Not quite sure about the spellings, but yeah. The third thing is called bounded staleness. Now this is a feature that is provided to us by some of the DBs. In this, you can just tell the DB whenever you make a read query to not ever give you data that is older than a few, let's say, seconds, right? You only want data that is like not older than 3 seconds. This will force the system to kind of give you new data. So again, this there are a lot of other ways as well. There is reading your own writes. There's monotonic reads. There's a lot of talk that I have to do about consistencies. There's not just eventual consistency, but there are other consistencies as well. There is something called a quorum. Now, quorum is a critical. It's a beautiful concept, in which is kind of better, honestly, than a lot of this sync async replication. So these are some topics that I want to discuss in future. But yeah, for this video, I think this is about it, man. And yeah, I guess, yeah, this basically covers all of it. If you have any questions, please feel free to ask me. And yeah, thanks for watching this. Bye bye.